For this is going to be recorded, and I'll just be using the whiteboard as normal to go through the content. So what we're learning about now is Newton's law of universal gravitation. That's what it's called, Newton's law of universal gravitation. And if you watch the video, Newton's law of universal gravitation tells us that every mass is attracted to every other mass. And the formula that we use is F equals big G m1 m2 over r squared, where that's the distance between them. So if we have two masses, right, this would be m1, this would be m2, and there's a distance between them here, we'll call that the radius. So that's our r squared. And as these distances get further and further away from one another, right, it changes. So like if m1's way out here and m2's over here, now we have a bigger radius, the force is going to be less. So the closer the things are together, the bigger the force. This is an inverse square law. And that means that the denominator is squared. Now, let's say we have a mass where, let's say we have the Earth. I'll make it blue for the Earth. There's the Earth. And we have an object up here, right? We have somebody up here. I don't know what they're doing, skydiving or something. So now our gravity, our force of gravity, F, equals big G. We got the mass of the Earth, mass of the person, that's this guy, and then the radius of the Earth, which is this distance, plus the height that this person's above the Earth. So it'd be the radius of the Earth plus the height squared. So it's the total distance away from where you're located. Just to let you know. This big G, that's the universal gravitation constant. And it equals 6.67 times 10 to the minus 11th Newton meters squared over kilograms squared. It's always the same. So that's a constant value, and you don't, to the negative 11th. You don't have to memorize that. That's something that will be given to you all the time, or you can look it up in your book during the test. So that's a constant value. Usually gravity is with big masses involved because of this constant. Notice to the minus 11th power, that's 0.000000011, right? That's a really small multiplier. So if the masses are small and the radius is rather small, or just a normal distance like a meter, right, you don't even feel gravity. So that's why we don't really notice gravity unless there's something huge like the Earth involved. Now, if we take this formula, I'm just going to use the mass of the person again over the distance squared. And let's say I have, here's the Earth. Let's do it in blue. I like to color coordinate. Here's the Earth. We got a person on top of the Earth, right? This person has a mass of the person, mass of the Earth. Remember weight? Weight was equal to mg, mass times the acceleration due to gravity. And we said this gravity, g, was negative 9.8 meters per second squared. And it didn't matter what the mass was. That gravity is negative 9.8 meters per second squared, regardless of the mass. And the reason for that is if I substitute weight, right, force is the weight of this person, or we call weight the force of gravity between the person and the Earth. So if I substitute this in here, watch what happens. If I take this mg, this is actually the mass of the person. So I have the mass of the person times g equals big G, mass of the Earth, mass of the person over the distance between them squared. These cancel out. And you can see our final formula for the acceleration due to gravity, g, is just g, mass of the Earth, over the radius of the Earth squared. Now, if I take this and solve it for g, right, let's just make a little math problem out of it. G equals, what did I say? Big G, mass of the Earth over the radius of the Earth squared. Now, we can look up in our book and find these celestial numbers on page 215. You can see the mass of the Earth is, where is it at? That's not the right chart, sorry. The right chart is on page, dun, dun, dun. It's probably on the front cover, right? I'm not even looking in the right spot. Man, I had it in the slide I was going to show you. The mass of the Earth is 5.97 times 10 to the 24th. So the mass of the Earth is 5.97 times 10 to the 24th kilograms. And the radius of the Earth, the orbital radius, I think is 6.3 times 10 to the 6. Pretty sure. I think I got the chart right here. No. Oh, there it is. So the radius of the Earth is 6.38 times 10 to the 6. So I was pretty close. 6.38 times 10 to the 6 meters. So let's put it in here and see what we get for the acceleration due to gravity. Do we get the 9.8? So G equals 6.6. I'm going to move this down because I'm going to run out of room because I'm writing so big. G equals 6.67 times 10 to the minus 11th. I'm going to leave the units out just for brevity. Times 5.97 times 10 to the 24th over 6.38 times 10 to the 6 squared. So when we put this in our calculator, we better get pretty close to 9.8. This is a good exercise to make sure you know how to use scientific notation in your calculator too. I got 9.78 for my value for gravity. So obviously these numbers are taken out the greater decimal places when they come up with the 9.81 value, or we just use 9.8. Now make sure you can put that into your calculator, because that is key, that you can put it into your calculator with the scientific notation for this section. So we can find the acceleration due to gravity, G, at any height above the Earth, right? All we do is change our formula to G equals big G. That doesn't change. Mass of the Earth doesn't change. Radius of the Earth doesn't change. We just add the height in there and square it. And sometimes they'll get tricky and give you this height in kilometers. Always convert to meters. You'll see sometimes books, maybe your tests, maybe somewhere, you'll see that height given in kilometers, and it's very common to do that and then try to trick you. So make sure that you convert that into meters. So that's how you find G. Does anybody have any questions there? And this is 6.5, just these two equations, that's it. It's our last study of forces, so it's our last force really. So our first question is, what is force of gravity between Earth and Moon? How big is that force? You think it's a big force? You think it's a small force? On page 1252 in your book, they give you the values, but I'll write them down for you. The mass of the Earth we just had is 5.97 times 10 to the 24th. The mass of the Moon is 7.35 times 10 to the 22nd kilograms. And the average orbital distance is 3.84 times 10 to the 8th. Oops. All right, try to find the force of gravity between the Earth and the Moon if this is your given information. And give me the thumbs up when you think you're done. I can turn my video off so you don't have to stare at that craziness there. Oh no, I just lost the whiteboard too. Hit the wrong button. I don't want to do that. Sorry, we just lost the button. All right, I'll just cover it up. There you go. You can look at the Golden Gate Bridge. I gotta get a better picture too. All right, I got some thumbs up. Let's take a look, see at this one. We want to find the force between the Earth and the Moon. So we're going to use the formula F equals big G, mass of the Earth, mass of the Moon, over the radius squared. So big F equals 6.67 times 10 to the minus 11th. Mass of the Earth, 5.97 times 10 to the 24th. Mass of the Moon, 7.35 times 10 to the 22nd. And the distance, 3.84 times 10 to the 8th squared. And I think it comes out to be 2.0 times 10 to the 20th. I'm almost positive. That's what it comes out to be. But I put it in my calculator anyway, just to make sure. Yep, 1.98 times 10 to the 20th is what I get. So there's a huge, what's that?
Question. Where'd you get the 6.67?
That's G, that's the constant. This G, that's the constant that equals 6.67 times 10 to the minus 11th.
Oh, that's at the top of my page. Oops.
Yeah, that's okay. So this is a huge number, right? 198, and then what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 zeros after it. That right there is the force between the Earth and the moon due to gravity. Big. So to keep that moon in orbit, you have to have a gigantic amount of force. And that's what we have here. Does anybody have any questions on that one? Could you get that into your calculator? Does anybody need any help getting it into their calculator? That's the tricky part for some people.
Give me 1 second.
What's that?
I said, give me a second.
Oh.
The last one, I don't know if it was because I put it in wrong or if it was because the number was just too big, but let me see if about this one.
Okay, I'll give you a second.
Would it be possible to just lop off some of the zeros? Like if you have 20 zeros and 22 zeros, you could just have 1.98 divided by like 735. I mean, if it was only those two things.
Well, it's squared, so you don't want to mess around with that. You know what I mean? But
Right. Oh yeah, but yeah. I'm just saying, like, we can always look at the exponents,
yeah, and then just subtract them.
yeah, to get smaller numbers in the calculator.
All right, after adding in the G, I did come up with the same number.
Good. That helps.
I'm good too.
All right, let's try another one. Why don't you guys try number 33 on page 223. It says the acceleration due to gravity at the North Pole is 9.830 meters per second squared, and the radius of the Earth is 6,371 kilometers. Find the Earth's mass. Give that a try. All right, so let's take a look at how this one's done. So this time we're using this formula, G equals big G, mass of the Earth over radius squared. And the radius is given in kilometers. So the radius here is 6,371 kilometers. So that's 6,371 times 10 to the third meters, or 6.371 times 10 to the 6 meters. We're trying to find ME, so we cross multiply. The mass of the Earth equals GR squared over big G. They gave us G in the problem to equal 9.83. And we just plug it in. And the mass of the Earth comes out to be, oh, it was close to what we think it is. .98 times 10 to the 24th. So we did good with our data. Does anybody have any questions there? All right, next question. What is acceleration of gravity on the surface of the moon? And this is number 35B in your book. So those of you who don't have a book, what's the acceleration of gravity on the moon? And the moon's data, if you don't remember from earlier, is 7.35, the mass of the moon. I don't know why I put it right in the middle of the screen. The mass of the moon is 7.35 times 10 to the 22nd kilograms. And the radius of the moon is 1.74 times 10 to the 6. Oops, I just changed that color midstream. And then for part B, once you get this, what is G at 6 kilometers above moon? So we find it on the surface and 6 kilometers above. Give those two a try.
For the mass, is it 735 or is it 7.35?
7.35. Yeah, 7.35. Sorry, got a little sloppy there.
And the big G is gonna stay the 6.6, or is that only for Earth?
No, big G is the constant anywhere in the universe. It's the universal gravitation constant. So it's always 6.67 every time, everywhere. All right, are we ready? How are we doing?
I just got the moon. I still need to do Mars.
Oh, don't worry about the Mars one. We're just doing moon, and then we're doing the 6 kilometers above the moon. Anybody give me the thumbs up yet? One thumbs up. All right, couple thumbs ups. I'll go ahead and give it a try. So the gravity above the surface of the moon, G equals big G, mass of the moon over the radius of the moon squared. So 6.67 times 10 to the minus 11th times 7.5 times 10 to the 22nd over 1.74 times 10 to the 6 squared. Gravity on the moon, I think it's close to 1.67. I mean, that's usually what's generally accepted. .65 I got. Gravity of the moon equals 1.65. That's meters per second squared. And then 6 kilometers above. So then the gravity is going to be 6.67 times 10 to the minus 11th times 7.5 times 10 to the 22nd over 1.74 times 10 to the 6 plus 6,000. Let's see if gravity changes much when we go up 6,000 meters. So 6,000 meters, what, I mean, that's what, 18, 20,000 feet? Um, 1.64 I got. Is that right? Is that what you guys got?
I got 1.69.
Well, it won't go up. You can't have more gravity.
Got 1.61.
Oh, I think I put it in wrong. Let me try again. It's got to be lower because we're higher in the air.
I had 1.619 for the surface and 1.608 for the 6 kilometers above.
Yeah, that's actually what I got too.
Is that what you meant to tell me when you said you had 1.7 or 1.69?
Yeah.
Gotcha. I got 1.64 again. 6.67, 7. Oh, I used 7.5. You see that? I screwed up. It's 7.35. That's where my error was. So this comes out, would you say 1.69, and this one comes out to be 1.61? Sorry about that. I was doing it right. I just put the wrong value in. I'm sure that's never happened to any of you on a test or anything. That was a joke, but it's hard to have a joke on Zoom because you can't see anybody. So anybody have any questions here? Good, I think. Final question. There was a fun question like, how high must you climb to lose 5% of your mass if your mass is 100 kilograms? How high must you climb to lose 5% of your mass if your mass is 100 kilograms? So let's get our mass Earth data. Mass of the Earth is 5.97 times 10 to the 24th.
Would it be 5% of your weight?
Does it matter? I guess you can't lose mass, right? Is that what you're saying?
Yeah.
I like it. I like your thought pattern there. Very precise. How's that? Is that better? Pretend
Yeah.
that never happened. I'll just go back and delete that from the recordings. 6.37 or 6.38 times 10 to the 6. That's the radius of the Earth. Now, here we are on the Earth. Oh, that's right. I'm making the Earth blue. And we got to go up to some height up here, right? We don't know how high it is. So that's the height above the Earth. So we have the radius of the Earth. That's from here to here. That's an R. The radius of the Earth and the height. So when we set this up, our weight, so the force that we have is 100 times 9.8. That's our weight. Weight equals mg. So 5% of our weight, we're trying to lose 5% of our weight. So F is equal to 980 times 0.95. So that'd be 5% of our weight, right? So now we're 931. 931 newtons. So if we're 980 newtons on the Earth's surface, right, that's where G is 9.8 on the Earth's surface. We're trying to lose 5% of that. So you can do this, 931, because we know that this is Earth's surface. So now when we set it up, F equals, I'm going to run out of room. I got so much going on here. I'm going to erase this terrible picture. Do it in blue, separate it. F equals big G, mass of the Earth, mass of the person, over the radius plus the height squared. Our goal is to find H. So we got to cross multiply. R plus H squared equals big G, mass of the Earth, mass of the person, over F. We're going to have to square root now. I'm going to move it over here. R plus H equals the square root. There's no way I'm going to have room on this page to do this. ME times MP over F. R equals the square root. Oh, we're looking for H, sorry. H equals the square root of G, mass of the Earth, mass of the person, over the force, minus the radius. That's our fun-filled algebra right there. So let's go to a new page where I have some room. H equals the square root. Oh, I shouldn't have put a tail on that. I'm going to do it first. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24th. Our mass is 100 kilograms. What was that force? 931? 931. Take the square root of that whole thing and then subtract the radius of the Earth, which was 6.38 times 10 to the 6. And that will give us the height we got to go to.
Now this is gonna be a dumb question, but why did you multiply 0.95 by the weight?
Because we're losing 5%. So our weight's 980 pounds. Wait, we could have done 5 times that and then subtracted 0.05 times. So what's that come out to be? 49 pounds or 49 newtons. So 5% of our weight is 49 newtons. So 98 minus 49, 980 minus 49 is 931. But if you multiply it times 9.95, that's the weight that you have left. Does that make sense? Instead of subtracting?
Yeah, it makes sense. Less steps.
Yeah. Do you understand where it comes from now?
Yeah.
All right, back to the calculator. I got 1.6 times 10 to the 6 meters, or to the 5th, sorry. One 1.6 times 10 to the 5th meters. So essentially 160 kilometers. That's pretty high up above the earth, 160 kilometers. Right, how many feet is that? What is it? 1 meter has 3.281 feet in it. There's 1 kilometer has 1,000 meters. 1 meter has 3.281 feet in it. There's a lot of feet. I could have just done it off the 1.6 times 10 to the 5th, I guess. 525,000 feet. So that's pretty high up. You're not hiking that high. Does anybody have anything need clarified there? Do we get it? All right, that's the last problem we're going to do. So I'm going to stop the video. So on the test, everything that we've gone over since the last test is going to be on there.
Okay.
Remember, this test is not just like remember the last one was pretty easy. It was just the quiz questions again. This one will have original questions on it. You will be more challenging than the last test. And we're submitting it to turn it in again.
Is there for Turnitin, like, is there a certain file that is recommended? Because last time it didn't work. I just sent you it email, but
What kind of file did you use?
I used a PDF and then I also used like a Word doc.
There's something must have went wrong because that's usually what they take.
Yeah.
I don't know what happened.
Yeah.
It should be seamless. I mean, that's their whole job, turn it in.
Yeah.
Does anybody have any other questions about the test?
Not really a
Anyway.
question about the test, but this was a lot easier than the last 2 classes, that's for sure.
Good. Yeah, friction's probably your hardest class in this chapter. All right, everybody. Well, if you have any questions or anything, let me know.